interesting format. Okay, so thank you for the opportunity to speak. So I'll tell you about this recent paper with Syk at the University of Amsterdam, which is about trying to make some connection between spin glass physics and holography. And yeah, of course, I'm coming from the holography background, so the idea is to introduce this topic to some extent and phrase it in a way that's hopefully more familiar to the audience. So I will start with a brief review of some relevant concepts, and then I will tell you in detail about this particular model of a spin glass, which is in some respects similar to the Syk model, but of course has other features. In particular, I'll be talking about replica symmetry breaking, which is the mechanism underlying this glass phase, and I will focus on various conformal limits of this model. And in the end, I will talk about out-of-time order correlation functions as a measure of quantum chaos, and we'll get back to holography. So yeah, so I think looking at the audience, I think I can almost skip these first few slides. So let me just show them very briefly to remind you of some of the concepts that will be relevant. So for those of you who come from this Syk type background, I just want to recall the following features. So the Syk model is this disordered quantum mechanics, Majorana fermions, which is solvable and serves as a toy model of holography in this strong coupling limit. The couplings are these randomly chosen disordered interactions. Now, the reason this is nicely solvable is that at large n it simplifies and can be formulated in terms of these bilocal mean field variables, which are two-point functions that are bilocal in time. In particular, in the large n limit, you get an effective action for these variables, which is essentially classical, and which becomes particularly simple in the strong coupling limit, where the effective action develops an FS1 reparametrization symmetry that is spontaneously broken by this, well, what I wrote here is the zero temperature solution, which is the conformal solution, and only preserves an SL2R. And the symmetry breaking pattern underlies much of the physics that shows up here and that we'll discuss later. Now, because this symmetry is spontaneously broken, you can do these reparametrizations, and they cost a little bit of action. And the action is the Schwarzian action that you've probably all seen, that describes the fluctuations of this reparametrization mode, and provides an effective theory of the low temperature dynamics of the dynamics in this particular limit of the model. And it's attracted a lot of attention because it also shows up as the boundary description describing particular type of dilaton gravity in ADS2. So okay, one thing that follows from the symmetry breaking pattern that will play a role later is that you can understand many aspects of the thermodynamics, of the low temperature thermodynamics, from symmetry arguments and from this kind of structure. So one example is the entropy at low temperatures, which has this extremal piece, and then it has a piece which is extensive in n and linear in the temperature. And this piece is described by the Schwarzian action. And so it follows from the symmetry breaking pattern. And another feature that makes the connection with gravity that we'll get back to is the fact that the Schwarzian describes an enhanced contribution to four-point functions in this model, in particular to the out-of-time order four-point functions that quantify chaos. Now, yeah, I guess I also have a slide on this. Let me be very brief because you're probably familiar with this. That the notion of chaos that's relevant here is this idea that, so it's a quantum notion that has to do with quantifying how chaotic the time evolution is, the Hamiltonian. So you evolve backwards in time, insert a simple local perturbation, and evolve forwards in time. And if the time evolution is sufficiently chaotic, then even if this is a very simple perturbation, it grows into a very complicated operator under time evolution that commutes with almost nothing else. And one way to quantify this is to compare these two states, where you insert the two different perturbations, one at time 0 and one at time t, and you compare what's the difference between inserting them in different orders. And to compare these two states, you can compute this overlap, which is this out-of-time order 4-point function that we'll be looking at later. So the statement of chaos in this context is that if the time evolution described by this e to the iht is very chaotic, then this overlap decays quickly, and these two states become very different. Now the Schwarzian theory I had previously gives you a contribution to this 4-point function that is enhanced at large beta j, and you can associate a Lyapunov exponent with it in the sense that this contribution grows exponentially with some exponent which satisfies the bound of the Zinashenko-Stanford, which is of course the signature that this is connected to black hole physics. Okay, let me know if I should say more. Now let me say a few conceptual things about spin glasses before I define the model for you in detail. I want to say a few general things about what's the phenomenology. So I'll discuss in a minute a model that's a bit similar to the SYK model at first sight, and the rough idea will be to replace the Majorana fermions by bosonic spins, sigma I, and you can think of them as living on as being the coordinates on an n-dimensional sphere. So usually we call it rotors. Yeah. Okay. Okay. I'll try to call them rotors. The original SY paper. That was what was given it. The previous work had all been on rotors, and then we looked at the kind. Yeah, I understand. Okay. No, I agree. I'll try to. Well, anyway, there are just some bosonic variables, and because they're bosonic now, you have to, for this model to make sense and for the potential not to run away, you have to impose a constraint that they live on some sphere. So what this means is that the size of that sphere is essentially another parameter, and we now have there will be two parameters in this model. So there's beta j, which is still measuring the strength of thermal fluctuations, and then there will be mj, which comes from the size of this sphere that we impose, and that will serve as a measure of the strength of quantum fluctuations, roughly speaking. Now, what happens in this kind of model is, of course, that because you have these disordered, this quenched randomness, these random interactions, that all the spins are subject to different random interactions that point in different directions, and they all try to minimize their energy. But of course, they can't, and the free energy landscape is going to look very complicated. So this is some cartoon here of what the free energy landscape might look like. So there's lots of minima and maxima and valleys and basins and so on, and the system slowly moves through this landscape and tries to find a minimum. But the basic idea is that there's a lot of metastable states, and in these spin glass models, what happens is that below some temperature, there's a transition where the system gets stuck somewhere, basically. So they gets stuck in some metastable states, and the dynamics slows down over many orders of magnitude, and everything becomes frozen in some sense. But, yeah, we'll see an example of that in the next slide. So we'll get there. So it'll turn out that there's a gapless theory describing the situation. So, well, we'll get there. They have a kinetic term, yes. I'll write down the action in a minute. This is just some introduction. So here I just want to talk about how do you quantify this kind of physics, because of course this is very complicated. So you need some useful mean field way of describing the structure, and a useful order parameter that you can use to characterize this phase is this Edwards-Anderson parameter it's essentially a sum over the average fluctuations but squared. So it's important that you square them. So this is essentially a 2-point quantity. If you didn't square them, then after averaging you would just get 0. So that would not be a good order parameter. I'll refer to the phase where this parameter is 0 as the paramagnetic phase, which is going to be somewhat similar to the Syk model in some respects. So that's the averaging. So there's a thermodynamic. Yes. Yeah. Oh, yeah, they're just real numbers. Yeah. N of them. Okay, and this order parameter being positive is going to signal the transition to this glass phase. Now, more physically, how can you see this kind of order parameter? So one way to see it is to actually look at 2-point functions, dynamical 2-point functions. So here's an example where plot this real-time 2-point function of 2 of the spins at fixed temperature, and going from top to bottom, we're getting closer to this dynamical transition into the spin glass phase. So in this top picture, we are far above the transition, and so the 2-point function has some behavior that has to do with quantum fluctuations being strong, and it decays. Then, as you get closer to the transition, you see that the decay becomes much slower. So yeah, it has some interesting structure. So you can sort of see that there's some 2-step procedure here. That it first decays to some plateau value, and then there's some long decay that stretches out over longer timescales. And finally, as the system goes beyond this dynamical transition to the glass, it never leaves this plateau value anymore, at least in the approximation that I'll be talking about. So it decays to some plateau value, and which is precisely this u that we had on the previous slide, as you can see from this for large t, and it never decays from that. So the dynamics sort of freezes. Okay, so that's a sort of one way to see where this parameter comes from. Yeah, there's some yeah. Okay, so the goals for this talk will be to characterize this phase, characterize some of these features, and so to some extent that's going to be a review of things that have been known for some time. So this kind of slow dynamics and the fact that there's many metastable states, and the system takes a long time or is unable to reach equilibrium. What does this mean exactly? And then we want to see how does this impact the low temperature thermodynamics and other characteristics that we got interested in over the last few years, such as these 4-point functions. And then I'll also talk about the symmetries that emerge and whether we can somehow incorporate this in this holographic paradigm involving ADS2 or merely ADS2. All right, so I'll be now more specific about what this model is that I'll be studying. So here's so this part is like the Hamiltonian with the random couplings. And I'm going to put P of those spins there. So this P is what you call Q in SYK. Then there's a kinetic term, and then there's this spherical constraint saying that these spins, these rotors should lie on a sphere. We impose that with a Lagrange multiplier field, Z. Minus N. So, yeah, so you could, yeah, if you want to see that the sphere has to do with M, you could redefine, you could rescale these guys to make the kinetic term canonical or something. And then, yeah. So you can push around the parameters, but in the end, there's going to be two-dimensionless quantities that are free parameters. Okay, so it's a nonlinear sigma model with a spherical target space, and the spherical constraint is very, very crucial for the model to be stable. Now, the first thing you want to do with this kind of model is you want to compute a free energy and an effective action that describes the large N physics. So what we have to do is perform the disorder average of log Z, where Z is the thing on the previous slide. And P is, say, some Gaussian distribution for these J's. And of course, the problem is how do you compute log Z? And we do what the strategy I'll be following here is to use the replica trick. So we write log Z in the usual way. And then all we have to compute instead of the logarithm is powers of Z disorder averaged. Now the powers of Z, so we have the same partition function here, but now with additional replica indices, which are these A indices here. So we now have little n copies of the system, and we'll keep track of their indices. Now we do the same thing as on this first slide about the SYK model. We introduce a bilocal collective variable that I'll call Q. But this was called G on the first slide, which is this two-point function, this two-point function with replica indices A and B. And after you integrate out the disorder and the spins, you get an effective action for this Q. What I wrote here is the Schwinger-Dyson equation that you get from that. And yeah, if you're more familiar with the SYK model, let me emphasize some of the differences. So one thing is that we kept track of the replica indices. The reason being that this replica of diagonal terms can be non-zero, and that's going to be the effect we'll be interested in. The other thing is the kinetic term, which now has so it's a two-derivative term and has a coefficient m that is a parameter, and we have a Lagrange multiplier field Z, which also enters in this equation, which is responsible for imposing the spherical constraint. Now, to solve this equation, you can make an ansatz that goes back to Parisi. And I drew here the simplest form of this ansatz, which turns out to be completely sufficient for this kind of model. So for this particular model, this ansatz is the most general thing you need, which makes it simple in some sense. So there's other spin class models from which we need more complicated ansatz. So what does this do? So this is an ansatz for the structure of this two-point function in replica space. So the indices of this matrix are the AB indices labeling the replicas. And we put some time-dependent two-point function QR along the diagonal, and then we add to it this constant matrix that is filled with blocks containing this order parameter U. Okay, so along the diagonal we have this QR plus U fields, and off the diagonal we just have U. You can also fill the rest with some constant S, but the equations are such that you can consistently set S to 0, so we won't worry about that. Now, tau minus in Euclidean? In real time or Can you clean?
Well, okay. Oh, right.
Yeah. Okay. Yeah, we'll
So there is no.
okay. Yeah, we'll see the behavior of this function in the various phases. Now the point is we have more parameters now, so there's not just, so we have made an ansatz, so the replica structure is now what it is. But we have a time-dependent two-point function, and we have this parameter u that we have to solve for. That's going to be determined dynamically. And we also have a parameter m that determines the size of these blocks. So that says that there's clusters of replicas that have the same overlap. And the size of these clusters is some number m, which we also need to determine somehow. And in the end, we want to take the n to 0 limit, right? So in the end, we take n to 0, and we need to, and the trick is going to be that m stays some finite number, and in the end, it's going to be between 0 and 1. So yeah, okay, that's the usual replica trick magic. Yeah, you can analyze the classical model. Like,
the original equidistant model required additional steps.
Yeah.
When you're working in the larger limit,
yeah, you can, in these other models, you need to give further substructure to these blocks, and like smaller blocks inside the blocks and so on. We don't need that here. Okay. Now, the Schwinger-Dyson equation we had here gives equations. So here on the top, you can expand that out, and you get equations for the entries of that matrix, Q and U in particular. So for this Q variable, this QR variable, which was the Q without the constant part U, you get some equation which looks like this, which perhaps looks familiar, where lambda is this self-energy type field. It's the thing that you would call sigma in SYK. And then there's additional algebraic equations for the 0 mode and for U. And one sticky point will be this parameter m for the block size. So how do we determine that? It plays no role when replica symmetry is unbroken, but in this spin glass phase, it has some non-trivial value. And one way to determine it would be just to extremize the action with respect to that parameter as well. I'll refer to that as the equilibrium spin glass, but as we'll see in a minute, this is not quite the right or the most physical thing to do. So there's going to be a better way to think about M, and it will not satisfy this extremality condition. And that's going to be a manifestation of the fact that this glass phase is not in equilibrium. That it's not in equilibrium, but in a very particular way. So I'll get back to this issue about M in a few minutes. But for now, let's just, you can just take these equations and solve them on the computer to figure out where this transition happens. Well, first of all, that it happens, and then where it happens. And you'll find some phase diagram that looks like this. So this is just a phase diagram where I also plotted the value of this M, which you can now see it takes a value between 0 and 1 after the analytic continuation. And so up here in this yellow region, temperatures are high, roughly speaking, and the quantum fluctuations, or this MJ parameter is small. So that's like a quantum regime. And the glass phase is what happens down here at low temperatures and large values of MJ. Now, of course, you can do all sort of, you can study this in various detail, and you can do thermodynamics and study the features across this transition and so on. What I want to focus on is the low temperature behavior. So like this region of the phase diagram down here, where we have some analytic control, and that's probably going to be useful conceptually. And so I'll very briefly talk about the low temperature regime up here in this replica symmetric phase. And then I'll say more about the low temperature analysis down here in the spin glass. And in both cases, there will be a sense. Well, okay, let me just do that. So let me start with the paramagnetic solution. So this corner up here at low temperatures or strong coupling. And let's ask if we can find a conformal solution. So replica symmetry is unbroken here. So the analysis is kind of similar at first sight to what you do in the Syk model. So you can study the equations at large beta j. And in this limit, you can neglect certain terms in the equations, and then the equations that you end up with have this reparametrization symmetry. So they're invariant under time reparametrizations, where Q transforms like a conformal field, like a conformal two-point function with dimension 1 over p. So the corresponding saddle point solution is this conformal answer. And from that, now you can consider the effects of breaking this symmetry, how the symmetry is broken, and that you get study fluctuations around this saddle and so on, and you find the Schwarzian action, and you can all do all these things. This is in the paramagnetic. Well, all I'm assuming here is large beta j. The point is, yeah. So here. However, this is not the solution we want. Yeah. So you can. This is a solution to the equations, but it's not physical. And yeah, one way to see that is that it doesn't dominate in the thermodynamic sense. If you just compare the free energies of these solutions with a different solution that you find numerically. Perhaps a more analytical way of seeing that there's something wrong with the solution is that you can consider what operators appear in this sigma OPE. So you can treat this like a conformal theory, and that would determine for you what operators or what 3-point functions you can have. So you can ask what 3-point functions are allowed by this symmetry between sigma I, and some operator with dimension h. So this is completely determined by symmetry, and gives you some equations that you can solve and that tell you what operator dimensions are allowed. So, and then you find some tower of discrete values of dimensions that are allowed. The lowest one being this h equals 2 mode. That is sort of analogous to sort of this universal contribution that's analogous to the stress tensor. And then you have these higher modes. But in addition, you find an operator with complex dimension. Okay, so this kind of operator shows up in this spectrum, and that's one indication that this solution is unstable. So yeah, and indeed the physical solution to these replica symmetric equations is a different one, as Subir says, which has a gap and so on. Yeah, so so this here is now the physical 2-point function defined numerically. So I plotted here the Euclidean 2-point function, and on the right-hand side I plotted the spectral function, related like this, at fixed temperature and for different values of this other parameter m. And you can see, so the typical case is like this yellow curve here. You can see that there's a gap, and this looks very different from this conformal solution that I described. Yeah, okay, so there's some more structure, but that's the rough picture. So now, mhm. Oh, not sure, we haven't quantified the gap. Yeah, well, somehow it's controlled by m, and yeah. So you can see here that sort of the gap gets smaller as you increase n, j, which means going closer to the transition. So this dark red curve is very close to the point where you transition to the glass. Far from the, yeah. Yeah, so then you have this kind of picture here. Okay, so this attempt to find a reparametrization invariant, a gapless solution in the replica symmetric phase somehow goes a bit wrong in this model. But now something more interesting happens in the spin glass phase, which is the one we want to understand eventually. So now I'll discuss the same large beta J regime, but trying to solve the equations with this replica symmetry breaking ansatz. And the way we get an analytic handle on this is by making another approximation, which is comparing in this 2-point function the constant part, this order parameter u, that is now finite, with the time-dependent part, and saying that in some strong coupling limit, it turns out that the time-dependent part is much smaller than this constant order parameter. So we can do another expansion in this parameter, and in particular we take this lambda, this self-energy, which is contaminated by all these constant u's, and we can therefore expand it for small qr. And so the simplest thing to do is just keep the leading term, so that this self-energy becomes linear in Q, and all the remaining powers of the 2-point function just become constants. Now, with this approximation, the equations of motion, you can solve them analytically, and what you find is some QR approx, so that some approximate solution, approximate in the sense that we have taken this truncation. So in frequency space, it looks like this. So let's see some features of this solution. So the first thing is that in a low frequency limit, if you look at the solution, it has this conformal term in it. So it starts with a 1. So there's a 0 mode. That's sort of the first term you get. But then you get a term that's linear in absolute omega. If you Fourier transform that, that's the scaling solution that we were asking how to find that. And here, what we see is that it looks like there's an operator of dimension 1, because it scales like 1 over tau squared. Now, moreover, this solution also behaves nicely at high frequencies, at short distances. So for instance, at high frequencies, it's finite. What this means is that we can consistently impose this UV boundary condition. This came from the spherical constraint, and it was a boundary condition to normalize the 2-point function at short times, to take this value 1 minus u, and we can impose that on this approximate solution because it's well behaved at high frequencies. So somehow this solution has UV and IR information, and in the IR it becomes conformal in this particular sense. And yeah, you can do more analytically. So you can, these expansions that I mentioned on the previous slide, you can expand all sort of things in this sense and determine these parameters like U or thermodynamic quantities and so on in a perturbative way. So let me just show some result, something you find. So what I'm plotting on the left is, again, the 2-point function. The full line is the numerical result to the full equations. And the dotted lines are this approximate solution. So you can see that in particular at down here, so that means for lower temperatures, the approximation becomes very good. And you can similarly use this approximate solution to compute the spectral density. And then again, it gives a very good approximation to the exact solution. And you can see that you can see the gaplessness of the solution. Yeah, and you can see the usual consequences of that in thermodynamic quantities, in the free energy or in the entropy and so on. So somehow this, in some sense, which I'll make more precise in a second, but it's a somewhat different notion of entropy. Yeah, so I'll get to that right now. So to do that, we need to get back to this issue about M, which was the size of the blocks in this replica symmetry breaking ansatz. So this conformal solution that I just described, because we can impose this UV boundary condition, that actually determines the value of M. And the value of M for which this solution exists and is consistent in the UV does not satisfy this extremization condition. So that's the sense in which it's not an equilibrium solution. And one way to think about this, so there's various ways to think about it, but one way that's perhaps interesting is to think of M as an external thermodynamic parameter, kind of like the temperature. So we want to think of M as something that's not, we don't determine that by extremizing the free energy, but it's a thermodynamic parameter. And one way to make that concrete is to consider a different ensemble where it's kind of like a grand canonical ensemble or something, where we consider M physical copies of the system. So before we even do the replica trick, we clone the system M times, so explicitly, and then on top of that we do the replica trick. But the blocks in that Parisi matrix that I had would now be physical copies of the system, where M is a parameter. Good. So if you do that, you can again compute the on-shell action, and you get essentially the same as before, but you get an upfront M. The on-shell action is going to be M times bigger. And now you can ask, what is the entropic quantity that you would compute from this? So if you do in the usual thermodynamics, what you would do from this on-shell action, which is the free energy, you could compute the entropy in this way. So it would be conjugate to the temperature. You can compute it as the difference of E and F. Yeah. Now in this ensemble where this conformal solution exists, we similarly treat M like M is now like a fugacity for F for the free energy, and the quantity that you get here, the sigma, which is the thermodynamic conjugate to M, is called complexity. So it's an entropy-like quantity that counts states, but in this slightly different ensemble where M is a parameter. And the states that it counts are all these metastable states in this free energy landscape. So this complexity counts the number of states that you have at some free energy F. And that thing, so you can compute this on shell or in this p-spin model, this rotor model, and you find some explicit answer that doesn't depend on anything but p. And this is in some sense analogous to the zero temperature entropy. It says that at zero temperature we still have some large number of states in this free energy landscape. I should say this is everything here these are all densities. So if I restore the overall capital N, then this complexity is extensive in N. So that entropy, that would be 0 to first order in these expansions. So for p equals 2, the model is kind of less, it's quadratic. So for p equals 2, like in SYK, you expect things to be quite different. Yeah, so we will, at many places, we'll see that things are often proportional to p minus 2. So this is sort of a mean field description. Yeah. Well, yeah. In what? In this low temperature analysis? Yeah, well, it's not. Yeah. Yeah.
What? This has been not a well understood issue, I would say. I mean, so finite range thick glasses, they're also there. Okay. The special picture is that there are only two different ground states. So each is gapless because they have various complex states with very different size. If in a range model, yeah, I mean, we found this gapless behavior. There are some investigations. All rearranged. Then each state. The spin glass order and the third infinity. And now you're in one state, one global space, one plus space. And in that state there are gaps. Not an entropy. Whenever
yeah, you can sort of combine them. This is, and in this sum, this physical entropy is 0, or it contributes some finite temperature terms. Okay, so let me take, yeah. Let me get to this thing about 4-point functions as another quantity that we would like to understand in this phase, just, see in what sense this might have a gravitational description or not. So what you have to do, okay, we'll do the out of time order 4-point function. A starting point is the Euclidean 4-point function. This doesn't look like it's, well, anyway, so the Euclidean 4-point function, it has some disconnected contribution, and we'll be interested in the connected piece, the 1/n term. And you can build that recursively from ladder diagrams, just like in Syk, which are the diagrams that have, at the corners, have these 4 spins, and then you add rungs to construct this kind of ladder, rungs of p-2 copies of the 2-point function. Now, something that's kind of interesting is that this kernel that you do this geometric series, this 4-point kernel has these offsets in the glass phase. So the 2-point function we already saw is offset by this parameter u, and now in the 4-point function, this red piece corresponds to the rails of the ladder, and it's also offset by some parameter v that it's of course built out of u, but provides some sort of 4-point analog of this Edwards-Anderson parameter. Now you can analytically continue this thing, this kernel, in the particular way with the correct boundary conditions, such that summing powers of this retarded kernel will give you the out of time order configuration in real time. And then what we're interested in for now is just the Lyapunov exponent, so the exponent describing the initial exponential growth of this connected contribution. And to extract just the exponent, all we have to do is solve this eigenvalue equation. So this is the growth condition that says that there's exponential growth. So this just says that adding one more rung to this ladder doesn't change the result. So the conformal symmetry sort of happens on top of that. Like in the 2-point function, we had that there was the u, and then the qr is the thing that has a conformal description. Yeah. Yeah, I think this is kind of spoiled by these u and v's. So. Uh-huh.
With the broken symmetry, you have to place, and the u is condensate, then there's a gap that's close from like voltage.
Yeah.
Normal, but yeah, there could be violations because of the condensate.
Exactly. Yeah. So. We'll do that in a second. Yeah. So there was this strong coupling limit where that's true. Yeah, but so for instance, something that happens in Syk, as you know, is that this kernel becomes independent of J. Right? So that is spoiled. That is depth, if you want. Yeah. So, but I think we'll understand this a little bit better, and when we try to solve this eigenvalue equation, for the kernel, analytically in this perturbative regime where both parameters beta j and mj are large. So I'll describe that very briefly, and then there's, of course, you can also, of course, just solve this numerically. So if you try to do it analytically, in this regime, where QR is much smaller than U, do essentially something like conformal perturbation theory around this approximate solution. So the approximate solution was the one that describes this conformal behavior, and you can now consider fluctuations around that, and try to solve this eigenvalue equation here analytically. And what happens? So you make an ansatz for the eigenfunction of that kernel, which exhibits this exponential growth. And the thing we want to find is the values of lambda L, the Lyapunov exponent for which this has a solution. If you make this growth ansatz, then the eigenvalue equation becomes a Schrödinger problem of this form. So it's a Schrödinger problem for this function f with this Cauchy squared potential. And the right-hand side you can think of as the energy level, the energies. And of course, this is a well-known Schrödinger problem, so we know what the allowed energies are, and they correspond to values of lambda L that are allowed. And the unique solution that's positive, so that shows exponential growth, is this thing in this box. So that's the fraction of the Lyapunov exponent compared to the maximal one. So a very compact way to write it is just a multiple of m, which was our block size parameter. But you can also expand it perturbatively again for large beta j and large mj. There's some double expansion you can do. And the leading order, it's linear in t. Again, it's proportional to p minus 2, meaning that for p equals, the quadratic model just gives you 0 in this limit. But perhaps worth mentioning is that also for other p, this goes to 0 in the strong coupling limit, so at 0 temperature. Okay, here's a more complete result that you get from solving the eigenvalue problem numerically. So this is again the fraction, the Lyapunov exponent in units of the maximal one, as a function of mj. So remember, small or large 1 over mj, so going to the right here, makes the system more quantum and takes you further away from the glass transition. And the glass transition happens here to the left. So here to the left of these dotted lines, those are values below the glass in the replica symmetry broken phase. Yeah, we see, so this plot has various interesting features. I'll not explain in detail, but roughly speaking, you can see that first of all, the Lyapunov exponent is non-zero, even in this replica symmetry broken phase. And in the paramagnetic phase above the glass transition, it also has some interesting structure because we have two parameters here, beta j and mj, and somehow the Lyapunov exponent depends on both of them in a pretty intricate way. So in particular, it has this peak at any fixed temperature. It has this peak as a function of mj, where you sort of achieve the locally maximal exponent. So the location of this peak sort of correlates with this transition we saw in the spectral function. That far to the right here, so far away from the transition, the spectrum was very gapped. And here further to the left, that's where the gap sort of gets smaller and eventually you enter the spin glass. And somewhere in between, these different effects compete, and there's some peak where the exponent becomes maximal. Okay. Well, so yeah, so I don't know what's the maximal exponent you can achieve anywhere in the phase diagram. So all these curves are sort of So the dark red curve is the largest beta j that I did here, but it's still not very large. So you would like to go further. But then it becomes more complicated to do the numerics. And I think what happens is that you keep having these peaks, and they keep growing closer to the maximal exponent. But at some point, the transition happens before you can reach the peak. So if you travel along these curves from the right, at some point you will enter the glass phase before you reach the peak. And
question you had on the previous slide, I was in some specific way.
So this was for the analytically, so that was for this regime. Yeah, so that's in the spin glass, and that's a regime that's perhaps a useful regime to study in holography. Certainly this large beta j part of it. Yeah, so there are some speculations I have here about what the holographic description could be. I guess I'll be very brief. And yeah, also, so this is sort of a proposal, but I'll be happy to hear your opinions. I'm not sure. We haven't really worked anything out here. So I'd be happy to hear if this makes sense or if this is unlikely to work. So the proposal is that this might have to do with this fragmentation instability that Juan studied, and it's been known for a long time, that ADS2 understood as the near horizon region of for the Weissner-Nordstrom, for instance, has this property that you can fragment into multiple ADS2 regions, and you still have an exact solution. So here is this example from Juan's paper. Yeah, this is a solution. Einstein-Maxwell in 4 dimensions. Yeah, and then and they are centered at some coordinates x1 and x2. And as you zoom in and go close to x1 and x2, you discover that there's actually two of these ADS2 times S2 regions. But from far away, it looks like the geometry looks the same as one that just has a total charge Q1 plus Q2. So the way you can distinguish them is by measuring something like a electric dipole moment or multiple moments. Yeah, this is schematic. So going up is sort of this x direction, roughly. So taking x close to x1 or x2 means sort of flowing down in this geometry and discovering these two. But it's, yeah. So yeah, so there's a moduli space of these solutions, because you have these parameters xi and the charges, and of course you can add more throats. You know, nothing stops you from stopping at 2. You can put more, and you have a freedom where you put them, and they're sort of diagnosed by an average dipole moment that we wonder if that's like this order parameter u that we had in this glass model. And of course, one of the questions is what does this complexity mean? How do you interpret that? And perhaps one can think of it as counting some sort of volume in this moduli space of geometries after regularizing it suitably. Yeah, and this dimension 1 operator that we observed in this spin glass strong coupling might have to do with with the moduli space dynamics that you can move around in this space, and the effective action describing this distance has no potential. Okay, we'll be happy to hear what you think about that. Yeah, already over time. I'll just leave the summary slide. Thank you. Yeah, yeah, it's probably a bit surprising, yeah, because it's a yeah, I know what to expect. I mean, this is what you find, but it's a the lore is that in the spin glass phase the system loses ergodicity and so on, so it gets stuck and it can't explore free energy landscape anymore. But yeah, so somehow there's still some modes that scramble. Yeah.
So if we try to take a look breaking in the boston bosons in the breaking in the replica space, replica is not continuous, right? It's used that you're breaking condensation in your
yeah, the U signifies that the symmetry that's really broken is the permutation symmetry among the replicas. Well, it's just it measures this self overlap or overlap between different replicas within a given state. So you have some cluster of replicas in some state characterized by this U. Yes.
The interaction is sort of you cannot think about the interaction as all the true, but
yeah.
If you look at the ratings, you really think that we have to kind of take it and that. It's all on magic of the analytic.
Yeah.
So you have this parameter m in the parameter, and you said it when it's between 0 and 1 when you take m to 0, right? But you didn't take m to scale with n, right? That's the part of the number. So if you do take m to the proportional to n, but take m equals 7 times that, and you find the thermodynamic
yeah, m has to divide n for you analytically continue.
But you don't take m over n.
No, you hold m fixed. yeah, I mean, yeah, so there's this alternative picture of this ensemble I described where M is something more physical, that you put M copies of the Hamiltonian. And then you do the replica trick on top of that. So that's perhaps that's more intuitive. So then you do replica trick on top of that with an extra n, and you take that n to 0 in the end. And then you have to see what value of m you get. It's this analytic continuation. Uh-huh. My understanding is that they're just that they're stable. You can put them wherever you want. And yeah. Some yeah, so this slide I had about sigma, most of that is general in the sense that you can do thermodynamics. Yeah, that's part of the question that we think when one could think about whether this complexity is a useful way to think, a useful notion in gravity or not. Yeah, I don't think we have the answer, but good question. Yeah, so some of them, there would be, like in this picture, there would be some moduli space of these solutions, and I think you have to regularize that space. It has some structure to it. Yeah, and you might wonder whether the volume of that space can be thought of in terms of this sigma. Mm-hmm. Yeah. Yeah, that's the idea. Yeah, so the thing that's left to count is the number of vacuums.